Okay, guys, we are going to continue. And the second part of our lecture is going to be about the type 2 of improper integrals or improper integrals with discontinuities. So we are going to just think about the same way of treating them as we did with improper integrals with infinite limits. Imagine that we do have a discontinuity here and we want to know the area over here. And sometimes this area can be finite, sometimes it's going to be infinite. So how are we going to treat this integral? We are going to pick up a point t over here to exclude discontinuity from the interval of integration. Consider this integral, right, which is going to be totally proper, and then bring our t as upper limit to the point where we want to kind of consider the integral. In this case, it's kind of 0, but can be something else. So I'm just going to write down 0, but you understand that can be something else. So by definition, improper integrals, if f of x is discontinuous at point B, then improper integral from a to b f of x dx is going to be equal limit as t approaches b from the left, integral from a to t f of x dx. What is this from the left? Well, if discontinuity happens at point b, if the function, for example, goes to infinity here, then we're not going to approach b from this side, from the right side. We are going to approach b from the left side. Sometimes different way to approach is going to give you a different limit because we are trying to cover our interval from a to b. Then we need to approach b from the left. But if you have discontinuity on the right side, on the left side, you are going to approach from the right. Otherwise, integral is exactly same way. I'm going to consider example. Example number 1 is going to be integral from 0 to 1 of ln of x dx. So how do we know that this integral is improper? Ln of x goes to infinity when x approaches 0. So actually infinity happens at the bottom of like our integral. So what I'm going to do, guys, I'm going to write down the limit and then integral of ln of x dx, and over here is going to t to 1, and t will go to 0, because my interval is from 0 to 1, and I'll need to approach this one because my ln actually looks like this, right? So infinity happens over here. I'm trying to calculate this area. It's going to be approaching from the right. Remember, left happens over here, right happens over on our side. Okay, so this one is going to be from the right. It's important, ln actually does not exist on the left, right? We know that there is no ln. So let's find this integral. We remember that to calculate ln integral, I will need to do integration by parts. A good time to review how we do integration by parts, right? I'm going to write down limit t approaches 0 from the right. And then integration by parts is going to give us, let's imagine that this is actually a product of 1 and ln of x, right? And 1 was actually a derivative because we are planning to differentiate. So this one is kind of g prime. And then g from there is going to be, if 1 is derivative, then g is x, right? So we are going to have x, ln of x, minus, sorry, I'm going to erase this thingy and write it down like over here, 1 multiplied by ln of x, and I'm going to put comma, g prime equals 1, then g equals x, right? Minus, now we copy g, and we'll need to differentiate ln, which is going to give us 1 over x dx, right? And we eventually going to get, sorry, I'll need to put limits everywhere, but let's put the limits at very end. Limit as t approaches 0 from the right, x ln of x, and here we just have 1, so it's minus x, and limits are t and 1, right? Let's do 1 first, upper limit. We're going to have 1 by ln of 1, 1 multiplied by ln of 1 minus 1, upper limit, then lower limit, t, ln of t plus t, because it has minus and the formula has minus also, right? And t goes to 0 from the right. Well, ln of 1, we remember, equals to 0, right? It goes through this point, equals to 0, actually. This is 1, and this is ln x. So here is 1. This is minus 1, not going to change. When t goes to 0, this one will go to 0. What is going to happen to this term? Well, guys, we are going to have like something going to 0 and something going to infinity. Say negative infinity, doesn't matter actually. We have indeterminate form, right? We're going to separately calculate what is going to be the limit. We already know what is going to be the limit, but let's calculate it separately. T, ln of t, because we already had it in our class, actually. 0 plus, right? So remember, when we deal with products, we'll need to convert them into ratios and then calculate indeterminate form. Remember also golden rule, logarithm never goes down. So I'm going to keep ln on the top. I'm going to put t in the bottom as 1 over t, and t will go to 0 plus. Now I have infinity over infinity. When t goes to 0, this goes to infinity, right? I'm going to use L'Hopital's rule. And L'Hopital's rule is going to give me derivative of ln is 1 over t, and derivative of this part is 1 over t squared, right? And I forgot the limit. Limit as t approaches 0 plus. Yeah, I'll need to simplify it, and that's going to give me limit minus t. If I bring this t up, I'm going to cancel with this one, and t goes to 0 plus is going to give me 0. Well, very nice. So this limit is actually equals to 0. So everything is 0 except the one term, which is minus 1. So that's our limit. So our limit is minus 1. So area here is finite area, and it equals to minus 1. Why it's minus 1? Because it's below x-axis, right? Negative areas. So in real world, we don't have negative areas, but in calculus, we do have, by agreement, that whatever is below x-axis is going to be considered as a negative area. Okay, very good. So basically all other integrals can be calculated this way. Now, what is going to happen if you have, example number 2, if you have actually discontinuity right in the middle of the interval? Let's consider example, integral from 0 to 3 dx x minus 1. You probably see that discontinuity is going to be when x minus 1 equals to 0 or x equals 1. So if you draw interval from 0 to 3, somewhere here is 1, and the function is not going to be continuous at this point because that's going to be a vertical asymptote, right? So we are going to have discontinuity. Same way we did with two infinities, we are going to treat it as two separate integrals. Integral on the first interval with discontinuity, integral on the second. I'm going to write it down as two different integrals. So we have integral from 0 to t1. t1 goes to 1, and because we are on the left side, minus, right? And then dx x minus 1. And then another limit integral t2 goes to 1 from the right and ends up at 3. And the integral is dx x minus 1. t2 goes to 1. Oh, I already wrote it over here. Maybe let me erase it from here. 1 plus t2. Well, we have two integrals. I'm going to calculate this one, okay? See what is going on. The same rule applies when you have two integrals. The limit exists or integral is convergent only when both are separately going to give you numbers. So if both are numbers, the limit exists. If only one is not number or both are not numbers, infinities, the limit is not going to exist, and we are going to consider the integral divergent. I'm going to deal with first integral and check if it's going to give me actually the limit. So 1 over x minus 1 is going to give me ln, right? We still remember this. Substitution of 0 and t1. I'm going to plug it in, and I have ln of t1 minus 1 T1 substitution, right, minus. If I plug in 0, I'm going to have a ln of -1, which is going to be a ln of 1 because we have absolute value. And that's basically why do we have absolute value here. So guys, what we have? This one equals to 0. T1 actually goes to 1. What is going to be a ln of 1 minus 1? Well, it's going to be 0. Ln of 0 goes to negative infinity, right? Goes to negative infinity, which means that integral is going to be equal to negative infinity. I'm not going to calculate the second one. I'm just going to write down that this one is divergent. Divergent because one of the integrals is already doesn't have limit. I'm going to write down first integral limit does not exist. Sorry. So you even don't need to calculate the second one. Second one probably exists. It doesn't matter. If one does not exist, we are fine and we don't need to calculate. So this one is divergent, means that there is no actually, we won't be able to calculate the area. Okay. So while practice with homework problems, they have more interesting integrals over there, and sometimes you will need to use L'Hopital's rule to calculate those limits, right? We are going to move to last part of this section, which is called a comparison theorem. Comparison. And this is the hardest part of this section, comparison theorem. Comparison theorem works for us when we cannot really find antiderivative of the function under the integral. You know that there are some functions which have antiderivatives which are non-elementary functions. It's not doesn't mean that they are not integrable. It's just like we cannot express it as a formula. So I'm going to write down like a general form over here. And because the theorem is relatively hard, maybe you kind of can watch this part a couple of times. So suppose that we have two functions. Suppose that we have two functions, f of x and g of x. And both are continuous. Both are continuous. With inequality true, f of x is greater or equal than g of x is greater or equal than 0. So both are positive and f is greater than g. Not everywhere, but for x greater or equal than a. We are going to work actually with first type and describe this theorem for the first type. Okay. Now, a, if integral from a to infinity of f of x dx is convergent. So if the top function has convergent integral, then integral from a to infinity g of x dx is convergent to. Looks like that if the area of f of x is a number, whatever lays down below that area is going to be a number too. B, if, second part, if integral from a to infinity of g of x is divergent, sorry, then integral from a to infinity of f of x gx is divergent to. Sometimes it's not very clear how it works, so I'm going to draw a couple of pictures here. I'm going to use a picture, choose a different color, to illustrate A. A. Let me get a picture. So this is f of x, this is g of x, this is f, this is g, this is point A. The theorem tells that if this integral is a number, then the one which is below is going to be just a smaller number. The one below cannot be infinity because that kind of you kind of see from the picture that it's supposed to be this smaller one plus extra is going to give you a number of the top one. That's why it's actually important to have all of them greater than 0. Now, go to a different color. Illustrate B. B. Again, F, G, F, G, number A. Now, guys, B is talking about the bottom one, and thus it's divergent. So the purple one, and it's not a number, it's infinity. Then what is going to happen to the bigger one, the red one? Well, because the bottom one, which is a part of the top one, is infinity, and this one is bigger than infinity, bigger than infinity, more than infinity, just because it's infinity plus something. Okay? So if the bottom is divergent, the top is divergent. If the top is convergent, the bottom is convergent. What is going to happen if the bottom is convergent? What can we tell about the top? Well, imagine that the bottom is convergent, not divergent, convergent number. Top can be another number which is greater than that number. It also can be infinity. So actually, when the bottom is convergent, theorem tells us nothing about like the top. Here, same. Imagine that the top is not a number, but infinity. If the top is infinity, the bottom of this infinity can be another infinity, just smaller, like twice smaller, infinity over 2. Or it can be a number, because both are going to be less than that infinity. So theorem doesn't tell you nothing when the top is divergent. Theorem tells us nothing when the bottom is convergent. So actually, divergent here is not going to tell us any information. Convergent here is not going to tell us any information. Only in this shape, it's going to tell us some information. And let's consider an example of how everything works. Okay, let's consider example. Example. I'm going to consider only maybe 2 examples. I don't know. Let's do example. Integral from 1 to infinity e to the power of negative x squared dx. You guys know that this integral, unfortunately, does not have antiderivative, which we can express as elementary function. We can either do it numerically or there is no formula actually. What we are going to do, I'm going to put non-elementary function. Non-elementary function. What I'm going to do, guys, I'm going to make a comparison. Here, it's important to understand how we make a comparison. We'll need to make a comparison on interval from 1 to infinity. I'm going to start with a small comparison of x less or equal than x squared. And x is from 1 to infinity. Why does it happen? I'm just going to draw the picture. You don't need to draw the picture every time. But here, picture is going to be essentially different starting from 1, right? This is x and this is x squared. You see that x squared is greater than x, and at one point is equal. Okay, what I'm going to do next, guys, if I put minus x and minus square, I'll need to change the sign of inequality. Now, if I put e to the power, I don't do anything with the sign because e is increasing function. Remember, if we apply increasing function to both sides of inequality stays. If we apply decreasing, e of x increasing. Increasing means that it goes like this, goes up. If we apply increasing function to both sides of inequality stays. If we apply decreasing one, inequality changes the sign. So guys, we do see that my e to the power of negative x is greater than e to the power of negative x squared. Now, what can I tell? Like I have my function. This is my f, and this is my g, right? Inequality, for inequality. Now I'm going to test, because I cannot test this one. I'm going to test this one. I'm going to calculate the integral. Integral e to the power of negative x from 1 to infinity dx. Going to be the limit, as t approaches infinity, I can integrate e to the power of negative x. It's e to the power of negative x. Remember that you differentiate exponential, you get exponential. Substitution of 1 and t, and it's going to be a limit t approaches infinity minus e to the power of negative t plus e to the power of negative 1. What is going to happen over here, guys? Infinity here is going to be e to the negative infinity. E to the negative infinity is going to give us 0. This one is going to give us what? 1 over e. So actually my top integral is convergent. So this one, because it's below g, is going to be convergent too. You will need to write down that by comparison theorem, integral g of x dx from 1 to infinity, which is going to be equal integral of negative x squared dx from 1 to infinity, is convergent to. Why? Because its top is convergent. We are in case A. This one is convergent, then the other one is convergent. You will need to write down this specific line, otherwise I won't understand, like, what do you mean, okay? So you have to say these special words by comparison theorem, okay? And sometimes the cases are going to be divergent. I think I'm going to consider one divergent case too, okay? Let me move it up. And example 2. This lecture is becoming too long. Example 2. Okay, integral from 1 to infinity, 1 plus e to the negative x over x dx. So guys, what I'm going to do, guys, I'll need to make a comparison to some function. And I'm going to make a next comparison. I'm going to say that e to the power of negative x is always greater than 0. Well, just a positive function, you know, any exponential function, if you don't have minus in front of the function, is greater than 0. Now, if I add 1 in this case, and I add 1 in this case, it's still going to work, right? Now, if I divide by x on this side and I divide by x on this side, it's still going to work. Why? Because I'm dividing by number greater than 1, both sides, the same number, it's positive number from 1 to infinity. So what kind of inequality I have? Well, if you look at this expression, it's just 1 over x. And this expression is what I have under the integral. So this is my f, and this is my g. F, my g. Well, I cannot estimate this, so I'm going to estimate this. I'm going to write down integral 1 over x dx from 1 to infinity is going to give us a limit as t approaches infinity, and 1 over x is going to give us a ln of x, right? 1, 1, and infinity, and we, oh, sorry, 1 and t, so put too many infinities, 1 and t, and we are just going to have a limit ln of t minus ln of 1 as t approaches infinity. This one goes to 0. This one goes to infinity. We remember that ln goes to infinities on both ends, right? This one negative infinity and this one is positive infinity. So we do have infinity, you see? So this integral is divergent. Now you are going to say by comparison theorem. Integral of f of x dx 1 to infinity, which is going to be what? Integral of 1 plus e to the negative x dx from 1 to infinity. is divergent to. But somewhere you will need to set up this inequality because this inequality is actually explaining why we can use comparison theorem. And sometimes in the book, you're just going to see actual integral here, and you can do it too. Just like if this one equals to infinity, then this one is going to be greater than infinity, divergent too. Now you probably tell me, how do we know? Like, which way to consider? Well, guys, how to make a comparison? I would say that usually to make a comparison, you will need to look how integral behaves at this special point infinity. If you look at this, for example, integral, what we have right now, we know that at infinity, this term, e to the power of negative x, will go almost to zero, and the integral is going to look like 1 over x. And we do know that 1 over x is divergent, right? Um, for this one, for the top one, let's look at this one. Well, here we know that at infinity, that's going to be e to the power of negative infinity, which will kind of go to zero, right? We remember that exponential function goes to zero at negative infinity. So this usually, guys, if you do a wrong comparison, eventually you are going to end up with a situation where you cannot use the theorem. For example, the unknown function is greater than convergent integral. And then you understand, well, it's greater than convergent function. Theorem tells us nothing because greater than convergent can be another convergent or it can be divergent one, which is infinity. Okay, well, I think that's all about this section. So guys, we're going to have our review on Wednesday as usually, and I think I'm going to end. We are done with integrals. Congratulations.